Welcome back to Calculus 2, Section 4.5, First Order Linear Equations. We're going to introduce the notion of a first order differential equation. We'll look at the general form. After that, we'll talk about the standard form. The standard form is going to allow us a nice way to solve. And then having solutions, we'll do some applications. Let's get started. So we're looking at first order linear equations. It's going to be first order if there's a first derivative involved and no higher order. And then the coefficient function on the first derivative is a function just of x. And then the y, the unknown solution, appears to the first order with a coefficient function, which is only a function of x. And if the sum of these two terms can be set equal to a function of the independent variable x, then you're looking at a linear equation. All right, so this is the general form of a linear equation. For example, a familiar situation of a free-falling body. Take a ball, suspend it in the air. It'll fall to the ground under the force of gravity. As it's falling, it will encounter the air, and the air will exert a force on the falling object in the opposite direction. Therefore, the total force is the sum of the force by air and the force exerted from gravity. Label that F total. Let's look at the two pieces. F sub air is proportional, that's the k, to the velocity, but in the opposite direction of velocity. So we can take the up direction to be the positive direction, the down direction to be negative. Gravity, on the other hand, is negative, has a downward direction, m for mass, and then g, 9.8 meters per second squared. Looking at this scenario, that for the air resistance to be proportional to velocity in the opposite direction, we need to assume that we're working with a small object. All right. Now, we have expressions for the two quantities on the right. The quantity on the left, we can use Newton's second law, mass times acceleration, and acceleration is the rate of change of velocity, dv dt. Now, looking at this, we have a first derivative on velocity. We have the unknown velocity appearing to the first order, and the m, k, and g are constants. Thus, this is a linear equation. All right, so the point is that linear equations occur in our natural phenomena, and thus are very worthwhile studying. All right, so we're noting that this equation is a linear equation. Go ahead and identify the independent variable x. So a linear equation takes this form. In our particular example, what is the independent variable? What's the dependent variable? And then identify the coefficient functions a, b, and c of x. Good. So we have a general notion of a differential equation. Let's talk about the standard form for a linear differential equation. Take the general form, and in the general form we have the solution function appearing only in the left, and then all terms that do not contain the solution function appear on the right. Now, we can take this general form and turn it into the standard form if we simply remove the coefficient a of x on the differential term dy dx by dividing both sides by a of x. Thus, b over a will term that p, and c over a will term that q. Good. So you have all terms involving y appearing on the left, and the coefficient on the derivative term is positive 1. And that would be standard form. All right. So we have an equation here. There's an unknown function y. A derivative of y is involved, and all the other terms involve x and constants. To put it into standard form, let's first begin by moving all of the y terms to the left, and then divide through by the constant 3, so that the y prime term has a coefficient of 1. All right, that's simple enough. And the point is that you can now identify the coefficient function p of x as the constant 1/3, and the right-hand side as q of x. And this is written down in standard form. Nice. Here we have 5 different differential equations. Identify which of the 5 are linear. And then if it is linear, write it in standard form to identify a p of x and a q of x. Very nice. Good. So we've looked at the general form of a linear equation, looked at the standard form, and the key thing in the standard form is that it provides you with the p and the q. And the p and the q we're going to see are going to be fundamental in coming up with solutions. And in the solution, what we need to do is come up with an integrating factor. All right, so let's start by writing down the standard form. Y prime plus coefficient p of x on y equals q of x. And then we're going to have this notion of an integrating factor. Take the standard form and multiply it by the integrating factor of mu of x. So each 3 terms is multiplied by mu of x. And notice that the way that I'm grouping, in the first term, I have a product of 2 factors, mu and y prime. In the second term, I have a product of 2 factors, one of the factors being the product mu p. All right, so looking at this standard form now multiplied by the integrating factor, you want to come up with a way of finding the integrating factor. And the way to do that is to treat the mu of x, p of x as mu prime. So if mu of x, p of x can be viewed as mu prime, then the nice thing is that this left-hand side is an exact derivative. This left-hand side, a product of 2 terms, if you think back to the product rule for taking derivative, is the derivative of the product function, mu times y. So that's really nice because we can then integrate in order to recover the unknown function y. Okay, so again, introduce this notion of mu, multiply it on both sides in order to come up with an exact derivative. It's still yet to be determined what mu is. But for the good mu, the integrating factor mu, we get an exact derivative and we integrate. Okay, so the expression on the right is going to be left as a formal expression. The expression on the left, we're going to be able to use the fundamental calculus to recover mu product y. Mu product y is then equal to the integral of integrand mu times q. And since we evaluated on the left, let's pick up a constant c on the right. And then we can isolate y by dividing through by mu of x. So what is the integrating factor? Well, we wanted mu product p to be mu prime, and the solution to that problem is that mu takes the form of the exponential raised to the integral of integrand p of x dx. What is p? P is the coefficient function of the unknown y. So this is why standard form is beneficial, is that it provides you with the integrating factor, and the integrating factor provides you with the solution to the problem. Excellent. Let's do an example. All right. Take a look at this equation. There's a derivative involved. It's a differential equation. There's the unknown to its first derivative and the unknown itself raised to the first power. Thus, this is a first order linear equation. First thing to do is to write it into standard form. Doing so will allow you to identify p of x. Quick quiz, what is p of x? P of x is negative 1 over x. Good. What do you do with that p of x? You use it to produce the integrating factor. How do you produce the integrating factor? You set mu, the integrating factor, to the exponential of the integral of p of x integrated with respect to x. So what's the integral of 1 over x? We're going to get the natural log of the absolute value of x. This is an indefinite integral. You pick the constant of integration to be 0. So you don't need to write it. We can use properties of logs to absorb the minus sign. And then we can use that the exponential and the natural log are inverse to each other to get that, let's make an assumption that the x will be positive, and therefore we can disregard the absolute values. And now let's use the fact that the exponential and the natural log are inverse so that we get our integrating factor as 1 over x. All right, so let's go back and look. We wrote it in standard form. Writing in standard form allows us to compute out the integrating factor. Now that we have the integrating factor, we're able to write down our solution. How can we do that? Well, y, the unknown, our solution, is 1 over the integrating factor. Note carefully that there are brackets on this binomial. What are the two terms? We have the integral of mu product q and a constant of integration. It's crucial that this constant of integration is appearing inside the brackets so that the reciprocal of the integrating factor must distribute onto the constant. Good. Now, what do we have for q in this situation? We have that q is x, and mu, we know that mu is 1 over x. Let's go ahead and take this formula with our q and our mu and plug them in. Reciprocal of the integrating factor out in front needs to be distributed on the integral of, that's integral of constant 1 plus a constant. 1 integrates to x, multiplied by x gives us x squared, and distribute the x onto the c. Fantastic. So we were given a linear equation, and we've come up with the general solution to the problem. What type of problem were we presented? A first-order linear equation. Very nice. All right, so here are some first-order linear equations for you to play around with. Write it in standard form, find the integrating factor, and then write down the solution. Good. So now we know how to solve first-order linear equations. Let's go and look at applications. We've already done one application, the free-falling body. Another application is electrical circuits. We need to introduce various notions. Let's go ahead and get that done. We want a closed circuit, so that's represented by this rectangle. Place in the closed circuit a voltage generator, something like a battery. So V sub S. We can introduce into the circuit a resistor, an inductor, and a capacitor. Okay, let's write a bunch of words down and then go back over these words in a second. A source of electromotive force, battery or generator, produces a flow of current in a closed circuit, and this current produces a voltage drop across each resistor, inductor, and capacitor in the circuit. Kirchhoff's loop rule states that the sum of the voltage drops across resistors, inductors, and capacitors is equal to the total electromotive force in the closed circuit. Okay, so let's go back over that. We have an electromotive force that's given in volts, capital E volts, and that's V sub S. Let's add that notation. And that there is a flow of current. The notation for the flow or current is lowercase I, that's I amps. The voltage drop across the resistor, our notation for that is E for voltage, sub R for resistor. That denotes the voltage drop. Across the inductor is E sub L. The voltage drop across the capacitor is E sub C. And then Kirchhoff's loop rule, with this notation that we have just introduced, can be written down as E, the electromotive force given from the battery, is equal to the voltage drops summed up across the resistor, inductor, and capacitor, E sub R plus E sub L plus E sub C. Okay, so put that to the side. Now let's go look at these voltage drops. So across the resistor, the voltage drop is proportional to the current I. So that's for the resistor. The voltage drop across the inductor is proportional to the rate of change of the current, I prime. Let's introduce notation for the proportionality constants for each of these statements. So for the first statement, we'll use capital R, the resistance, as the proportionality constant. For the second statement, we'll use capital L, the inductance, for the proportionality constant, for the voltage drop across an inductor. Good. All right. There was one more voltage drop that was across the capacitor, and it is also proportional to this new term, Q, And the Q is the charge of the capacitor. Very good. Now we need to relate back the Q and the I. I is the current, Q is the charge. The rate of change of the charge is the current, I. Nice. So we can consider two different configurations. Here's the first configuration that we'll consider: a closed circuit with a resistor and inductor is an RL circuit. So we want to come to the notion that an RL circuit can be described, can be modeled by a first-order linear equation. We're missing a conductor. Therefore, Kirchhoff's loop rule is stated in this equation: Li prime, the drop across an inductor, plus R times I, the drop across the resistor. That sum is equal to the voltage source, capital E. The L is a constant, the R is a constant, the E is a force, which is not a function of I. Thus, this is a first-order linear equation for the unknown function current. Very good. Let's look at a book example. The electromotive force is given by 50 multiplying sine of 20t volts. The resistor is of 5 ohms. The inductor is 0.4 henries. When we look at the voltage drop on the resistor, we have that the resistance is capital R equaling 5. Therefore, the voltage drop is 5 times I. The inductor is of 0.4 henries. Therefore, the inductance, capital L, is 0.4. And the voltage drop across the inductor is 0.4 times the derivative on the current. Plugging in this into Kirchhoff's loop law, we get a first-order linear equation. This would be in a general form. To write it out in the standard form, we divide through by 0.4 to come up with this form. Nice. We're told that the initial current is 0. That means that the initial condition will be that the current at time 0 is 0. And now we have a first order linear equation as an initial value problem. Okay, so the first thing that we do is identify P of t and Q of t. That's done, we know, from writing the linear equation in standard form. Having P of t, we're then able to come up with the integrating factor. We take the exponential of the integral of P of t. P is just a constant, so we get 12.5 t. The integrating factor is then allowing us to recover the unknown function, which in this case is the current I. So we've set up and found an exact derivative. And with the exact derivative, we can integrate on both sides. Very good. On the right-hand side, note that you have an integral, which is an exponential multiplying an elementary trig function sine. And this is a good opportunity to go back and review. integration by parts. There's a fair bit of algebra involved, but this is essentially an integration by parts computation. On the left-hand side, the integral of a derivative. That's easy to find the antiderivative. You just look at the function that you're taking a derivative of. And we know that we're interested in finding the current, so we isolate I of t by dividing through by the exponential. All right. The last thing to do is to fix this constant c. We know that that is done through the initial condition. And that's just a matter of plugging in and isolating the unknown constant c. Excellent. Now, when we take this constant c and we plug back in, we get a form that looks like this. They're allowing us to then, instead of rewriting this out as a difference of sine and cosine, if we manipulate a little bit, factor off this term, and then identify a cosine of some angle as 8 over the radical of 89, we can use the Pythagorean theorem to come up with sine of that angle, phi, as 5 over radical 89. And the 8 over radical 89 and 5 over radical 89, we can plug those in with sine and cosine of phi, and then use a sum identity for cosine to swap out this term, this sum and difference of sine and cosine, for a single cosine function. And that allows us to write the charge function as some amplitude on a cosine function, which has been phase shifted by the angle phi. And this second term is called an attenuation term. Note that it's just a constant on an exponential, which has a power which is negative. Thus, this term will decay. It'll decay quickly, and leaving you essentially just with this cosine term. That cosine term, if we look, is graphed out here for you. And remember that this system was such that the voltage force introduced was given by a sine wave, and that we've solved for the current, which is given essentially by a cosine wave. Nice. All right, so I mentioned that integration by parts is what you want to rely on to take this indefinite integral and evaluate it as this quantity. So in this assignment, go through that process. Here is a checkpoint problem from the book, and as a checkpoint problem, the solution or answer is provided in the book. And the example that we've just done was for an RL circuit. Another configuration is an RC circuit. Let's take a look at that. So a closed circuit with a force and a resistor as well as a conductor. And then Kirchhoff's law would say that the force introduced is the sum of the voltage drops. And across the resistor we have Ri, and across the circuit we have 1 over C, the capacitance, times the charge. Looking at this, we have two different quantities, an I and a Q, but we know that the I and the Q are related, that the I is the rate of change of charge. Now we can see that we have a first order linear equation. So both for an RL and an RC circuit, they can be modeled as first order linear equations. Good. So take this first order linear equation and solve for the charge in terms of the constants R, C, and the voltage function E. All right, that brings us to the end of the video. Thank you so much for watching. Please like if you find these videos useful, and I will see you on the next one.